go through as long as you'd like, and I can talk about some of the things that are going to be on the test tomorrow too. So y equals 1. y equals 1 over log base 2 of x. Okay? So this really depends on how you want to do it. But if I'm going to do this, I know my log rule d dx is going to be equal to, state the log rule, it's log base a of u, and the derivative rule is 1 over what you're taking the log of times the natural log of a, and hopefully everybody got that. I know everybody got the email, and hopefully you've looked at it now and made that correction in the notes, times du dx. Now, here's the problem. What do you see about the problem that's different than what we're used to? The denominator. The log is in the denominator, okay? Don't rip this one off because that's last week's and I hadn't put that extra credit in yet. Everything else is in the grade book except that very thing. I even got yesterday's homework in. But yeah, what makes this different is that the log is in the denominator. So what did we go over yesterday? And it's actually still on the board. It's Patrick's problem, number 4. To do a problem like this, what can you do to it? Move it to the top. Okay? You want to be able to use your log rule, but you can use it in the denominator, but you're going to multiply by the reciprocal. And if you do it and leave it in the denominator, what rule are you going to have to use? Have fun with that one. Okay? Have fun, quotient rule, and trying to multiply by the reciprocal. Alright, so what I'm going to do is I'm just going to go ahead and move it to the top so I don't have to use quotient rule. You understand, if you have it on bottom right now and you don't move it to top, you're going to use your log rule, don't worry. But you're also going to be using quotient rule. So anytime we have a constant in a fraction, try. You never should be, let me say it clearly. Anytime you have a fraction, and there's a constant either on the numerator or denominator, you should never be using quotient rule. You should be looking for a way either to use constant multiple, and that's when the constant's on bottom, or when the constant's on top, move it to the top, and then just use chain rule. Okay? So with that said, I'm going to go like this. I'm going to go log base 2 of x. Now, where do you put the -1 exponent? That's the question. If this was trig, I'd probably put it right here. But here's the problem with doing that right now, with trig, even with trig. If you do that, I'm going to just put in parentheses, do a patch set, and put a negative exponent around. Let's say this was a trig thing, and you had 1 over sine x. And we want to do the derivative of this, and we don't want to use quotient rule. You're not moving it to the top and calling it sine -1x, because that completely just changed the problem. Agreed? That made it inverse sine. What you're doing is you're either going sine x to the -1 to clarify this is not inverse sine, or you're just saying, wait a second, I know what the reciprocal of sine is. When I move it to the top, it becomes what? So just make that note on trig ones. You're probably just going to use the reciprocal ratio to move it to the top and change it into another trig function. So I just wanted to talk about that while we're doing with the log. But with the log, we don't have a reciprocal ratio. We don't have something we can change it into. So you are going to have to use the -1 exponent in that situation. So now that I got the -1 exponent in there, now I'm going to go y prime. You ready? Chain rule. It'll be -1 times log base 2 of x to the what power? -2. Now what do we do? Take the derivative of the inside. Now the derivative of the inside is log base 2 of x. So that means I'm going to use my log rule. So I'm going to go 1 over x times what? ln of 2 times the derivative of x, which is what? 1. Does that make sense? Okay, so then final answer, I just got a bunch of 1s on top with a negative, so I'm going to have -1 on top. And then the bottom, it looks like I'm going to have x ln 2 times log base 2 of x. And make sure the whole thing is squared. I'm going to move it to the bottom. And let's see there. Is that what we got? Yep, that's the answer. Any questions on that one? Okay, what else?
19.
19, okay. 19. Natural log of natural log x. So what?
Really? I didn't know we had.
Why?
It's 1 through 30 even. Oh God.
Are you serious? I meant to say all.
Well, I did it all.
Are you serious? I changed it to 1 through 30. I had 2 through 30 even. I was like, I'm not changing that. I'm just gonna make him do it all. So I changed the 1 through 30. I forgot to change the even into all. Dang it.
I was wondering whether one was in there. I wouldn't know if it's 30.
Oh, work should not have taken that long. I can do 19 though.
I need to read my notes.
19. Gosh, that's awesome. 19.
I'm like, why is this so much? Like, what the heck?
I wanted it to be so much. So, 19 just because. Okay? Alright, so how would you do this problem? What would be the inside part here, the most inside part? Even the more inside. X is the most inside part, but it's just plain x, and the derivative of that's going to be 1. The next layer would be natural log x, and the next layer would be the natural log of natural log x. So how are we going to do this? Start with what? The very outside part, which is the natural log. So we're going to have 1 over what? ln x. That's where it gets weird, though. We got 1 over ln x. Yeah, I don't need that. Never mind. It's not log base 2. I was trying to multiply by the natural log of the base, and I'm thinking, wait, natural log of e is 1. Okay, never mind. So it's 1 over what's inside the natural log times the derivative of the inside. Now, when I get to the derivative of the inside, I've got ln x. What's the derivative of that? 1 over x times the derivative of the inside, which is just what? 1. And so we end up with 1 over x ln x. Here's your derivative. What else? 30? Did you say 30? Yeah. Okay. At what point on the graph is y equals 2e to the x minus 1? Okay, y equals 2e to the x minus 1 is the tangent line perpendicular to the line y equals negative 2x plus 3. Now let's just, so we want to know where it's perpendicular to y equals negative 3x plus 2? Is that correct?
Yep.
So you want to find a point. Let's just visualize this. Okay. This graph is e to the x. What's e to the x curve? Come on, help me. What kind of a curve? J curve? Yeah, question.
No, that was my J.
Okay, oh, okay, J curve. So J curves usually start at 0, 1, right? But what happens to this graph? It shifted down 1. So now it starts at 0, 0, and the horizontal asymptote is at negative 1, correct? And then, so it looks like this. Okay? And then we have y equals negative 3x plus 2. That graph is up 2, and it has a slope of negative 3, so it goes down 3, right 1. So we have a graph that looks something like this. And I want to know where the tangent line is going to be perpendicular to that line. So it looks like, if I had to guess, it looks like somewhere around here I'm going to have a tangent line. Somewhat, maybe at 0, 0, I don't know. Tangent line that's perpendicular. Just make sure you put what type you got here. Perpendicular to this negative 3x plus 2 is perpendicular to this. Now, I'm trying to figure out the slope of the tangent line, and is really what I'm after. Okay? I know what the slope of this line is. What's the slope of this line? The slope of this line is negative 3. Does everybody get that? Okay, you get what we're trying to visualize. Anytime you do problems like this, if you can draw pictures to help kind of visualize what you're trying to do, it'll help you understand the problem a little better. Because I think most of you are probably like, okay, I think I know where to go with this now. If I know that slope's negative 3, what would the slope of the tangent line have to be? It'd have to be what?
1 over 3.
It'd have to be 1/3. So if I want to find the point where this tangent line is going to equal to 1/3, it's no different than when we did horizontal tangents. You remember how we found horizontal tangents? We took the derivative, set it equal to what? 0. I want to find where the slope of the tangent is going to equal 1/3. So what am I going to do? Take the derivative, set it equal to 1/3. Now that's going to get involved in solving a log equation, which is review, and some of you will have a hard time with that. But you'll remember when we see it. So what we do then is we have y equals 2x, 2e to the x minus 1. We take the derivative of that. What would the derivative be? Well, it's constant multiple rule. It's just going to be 2 times the derivative of e to the x. Well, the derivative of e to the x is just e to the x times 1, I guess. I only need the 1. And then the derivative of a constant is just 0, so there's your derivative. Your derivative is just 2e to the x. So now I'm going to set that equal to what?
0. Or not 1/3.
1/3. 2e to the x is equal to 1/3. What do you do now? Divide by 2, so it's going to be e to the x is equal to what? 1/6. What do we do now? Natural log of both sides. We're solving a log equation. I take the ln of both sides. What's the ln going to do to the e? Cancel, so we're just going to have ln 1/6. Now, let me talk about ln 1/6, because they might have that. Very possible they'll have that. It's also very possible to have negative natural log 6. Anybody tell me how I got negative natural log 6? Nope. Jacob? So, how does that help me get to negative natural log 6?
Because you're pulling 6 up.
Nope.
Yeah, we don't have a negative exponent.
Yeah, why is it being negative exponent?
6 to negative 1 power, you pull it up. Negative 1 over.
Nope.
6 to the negative 1 power.
Okay, so I agree with that, but I need a little more explanation.
How much more did he explain?
Yeah.
Oh, okay, I see what you're doing. You're automatically assuming, okay, when I bring the 6 up top, it's a 1 on top. Yes, 1 times 6 is 6, yes. So then it would be 6 to the negative 1, and then you can pull the monkey out here. There's another explanation. I kept thinking there was a different number there. I was wanting to multiply with the property. So if you move 6 to the top, it becomes 6 to the negative 1. Another way to do it, and the way that I was thinking about it, which is why I went tracking with you guys, is this is natural log of 1 minus natural log of 6. And what's natural log of 1? Well, you got to know that one. 0.
Gotcha.
Okay? But like what you guys were going at a different route. You can move the 6 to the top, it becomes 6 to the negative 1. There's already a 1 there, so it's just 1 times 6 to the negative 1. It's just 6 to the negative 1. And pull the monkey out 3, that works too. Okay? So you've got to be able to see that they might not have natural log of 1/6. And this value, this x value, negative natural log of 1/6, it said in the directions, it says find the point on the graph at where the slope of the tangent is going to be perpendicular to this line. All you found is an x value. What would you have to do next? Find the y value if you want the point. How do we always find a point? Original. No matter what, all year long, you have to find a point, it'll be plugged into the original. So you take the original equation, which is this, and plug it in, so you're going to have y equals 2e to the negative natural log, let's put it back as this, because it'll work out a little bit nicer. Natural log of 1/6, and then minus 1. Okay? Now, what happens when you plug in natural log of 1/6 into that exponent? Who remembers? Come on, this is on the gateway test like 1,000 times. Not 1,000, but you know. Yes, the e and ln what? Cancel, so we're going to have 2 times 1/6 minus 1. What's 2 times 1/6? 1/3. Now you're going to have 1/3 minus 1, which is what? Negative 2/3. There you go.
It just drops down.
Yeah, it just drops down. Yep, that's the property.
I was thinking it goes to the power of 2.
Any questions there? And that is correct. What else? Good problem. Like that. Thinking problem. It's not just brainless taking derivatives. So we're like, a derivative's brainless? Should be for you guys. Should just be able to do it. I didn't think about it. What else? Nobody's asking, did I have 37 to 42?
Yeah.
Nobody wants to know how to do those.
Oh, yeah.
So we had to state the domain of f prime.
Do 39.
39, okay.
Or was I not supposed to do that?
No, you're supposed to do
No, you're supposed to do that one. Okay, let me do an easier one first. I'll do 38 and 39, and then that should explain it. So 38, natural log So you have y equals natural log. Then we're going to shift gears. I have a couple other things I want to do. So 38 natural log of 2x plus 2. So the first thing I want you to do is, if you were going to find the domain of f prime, what's the first thing you have to do? It's the first thing you have to do.
Outside.
Well, you got to take the derivative, right?
No.
All right, so what's the derivative of natural log? What? 1 over 2x plus 2 times what?
2.
Times 2. Okay? So everybody got the natural log rule down now? And when it's log base a, all you got to do extra is multiply by that log a, or natural log of a in the denominator. That's the only extra thing. So we get y prime is going to be equal to 1 over 2 times x plus 1 times 2. What happens to the 2's? Cancel. So we get y prime is going to be equal to 1 over x plus 1. So they want to know the domain of the derivative. Okay, it says find f prime of x and state the domain of f prime. Now, a lot of people are going to jump the gun here and be incorrect, okay? What you need to think about is that the derivative is, this gets a little hard to think about because we haven't done a lot with it yet, but the derivative is based off the graph of the original. Would you agree with that? And if we go back to differentiability for a second, when we think about what differentiability is where the derivative exists. Okay, it's where the derivative is defined. Okay, and where the derivative exists is going to be where it's going to have to be based off the original function where it exists. And remember what I said about continuity? Continuity follows when you're going through the derivative. So domain's going to follow when you go through the derivative. So when you think about the derivative, the domain for the derivative, you also have to think about the domain for the what? Original. It is not okay to say here that the domain is going to just be x cannot be equal negative 1. And if you did that, that's not correct, which is why I cited these problems. I wanted to talk about differentiability a little bit. So the domain is not just x cannot equal negative 1. That's true, it can't. You're right, it can equal negative 1, can't get 0 on the denominator, but there's more to it. Because what I have to do is I have to consider the original function, what the domain for it was, and really combine the two domains. Okay? So, and you'll think about it, and it'll make sense here in a second because I'll graph it. What would the domain for the original function be? What can you not take the natural log of? You can take natural log of 1, natural log of 1, 0. Can't take natural log of 0, what else? Anything less than 0. Whatever's in here has to be what? That has to be greater than 0. Okay? So you're going to have to take 2x plus 2 and say it's greater than 0. And then what I'll get there is I'll just get x is greater than what? Negative 1. Now, if I take that with this, well, this already says x cannot equal negative 1. So if I combine these two domains and kind of see where they overlap, what would the official domain of the derivative be? And then I'll explain why this is. So this is not enough down here. I have to say the domain for f prime is going to be x greater than negative 1. Now let me explain why. Because some are like, well, I don't see why you're combining the domains. It'll make total sense when I graph this. If I was to graph this, it's really natural log of 2 times x plus 1, which is just the R curve shifted what? The R curve shifted what? Left 1, right? And left 1, I won't say right. Left 1, correct? And so it goes over here to 0, 0, right? Correct? And then the horizontal, vertical asymptote goes at negative 1, correct? And so then we draw this R curve, and the 2 just stretches it. And now, when you think about the derivative is the slope of the tangent lines. What slope of the tangent lines actually exist? Everything to the right of negative 1. Are there any slopes of tangent lines that exist before negative 1? So the derivative can't be defined before negative 1. Does that make sense? Okay? Like you can't have a derivative at negative 2. There's no point at negative 2. There's no slope of the tangent line at negative 2. You can't have a derivative at negative 3 because there's no slope of the tangent line at negative 3. You got to remember what the derivative actually is. So when we say the domain for this, we're saying This is where the original function is going to have slopes of tangent lines. It's going to have a slope of a tangent line only when x is greater than -1. So you're saying more about the domain. You're not just saying where the domain, because I know this thing right here has two pieces to it. But what part of it is going to actually tell you the slopes of the tangent line for the original function? Just the part where x is greater than -1. That's the one that would actually tell you slopes of the tangent line for the original function. That's a good problem to look at. So now we can look at 39. It's going to be the same thing. 39, we got natural log, we got y equals natural log of, what is it? 2 minus cosine x. So what I need to do is I probably need to consider the domain for the original function first. Okay, I need to consider the domain for the original function first. And let's see here. I don't even know what the answer is. Anybody look in the back of the book? Let's do it. So we have 2 minus cosine x is greater than 0. And so then we're going to get cosine x is less than, what would it be, 2? Is that correct? If I move the 2 over and divide by negative? Good? Does it say it's all right? What does it say for 39? Let's see. Sine over 2 minus cosine x. It's all real numbers. Cosine x is less than 2. I write the problem down there? I might have to look at this one myself, y'all. It's done one like this in a long time. Hold on a second. Perfect time to pause. That video's getting long. Pause.